Namaste, Mr. Bossert here. We're talking today about different base number systems, okay? And as we know, or maybe you may have never even thought of this, right? When you first learn, you learn math, you learn counting, you learn base 10, or the, another way to say that is the decimal system, all right? DEC is the prefix for 10. So you have a base 10 system. And, you know, why do we have a base 10 system? Well, probably because we have 10 fingers and 10 toes. That's probably when people started counting. I mean, that seemed to be a whole thing, a whole unit would be, 10 of something. That's one whole, because that we have to then start over. If we think about how we number things, right, we know that this number in here blue is 735. And if we think back to the 3rd and 4th grade, we had expanded notation. We know that it's 735. Your teacher would have made you write 7 times 100 plus 3 times 10 plus 5 times 1. And the reason we chose those, right, is because that's the hundreds place, tens place, ones place. And we learned those things. Why are those the places? And the reason is that we have a base 10 number system, and those are all powers of 10, right? Starting with 10 to the 0, right? That's 1. And so this is the ones place. This is the first place in decimal. The next one is, and again, what numbers fit into the ones place? Well, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 10. We don't have a number for 10, so we put a 1 in the next column, which is the tens place, or 10 to the first, and that becomes the tens. And then when we fill up and we don't have any more tens, we have 9 tens. We don't have 10 tens, so we go ahead over and we into the 10 to the second, which is 100. The next place is the 10 to the third place, which is 1,000. The next place is 10 to the fourth, which is 10,000. So the reason that we have those places is because it is the next power of 10. Well, we look at my friend down here, Homer Simpson. I don't know if you've ever noticed this before, but he has 1, 2, 3, 4 fingers on each hand, giving the Simpsons a total of 8. And really, if all people were like the Simpsons, first of all, scary. But the reason that we probably have base 10 is because we have 10 fingers. When they ran out of fingers, they ran out of toes. That was the next thing to do. But you can just as easily use, if we were the Simpsons, you could just as easily use base 8. Right? So there are different reasons for alternative counting systems. If we eventually encounter alien life or life from a different solar system or something, they likely will have a different counting system. It will operate much the same, as they would still have to count things and have mathematics, but it may not be a base 10 system. And in fact, something that uses a counting system all the time is computers, and they have, I think we understand, they have a binary or base 2 system. So I've got some text here. This is from other things, but wanted to tell you that the reason we have base 10 is likely because 10 made a whole group of something. It was just easy to start over once you got to that. And again, if we were the Simpsons and we had base 8, we might likely be a base 8 system rather than a base 10. So again, we know 0 through 9 are the numbers in our base 10 system. There are 10 digits. We call them digits because it's decimal, but there are 10 different numbers that fit in our system, 10 symbols, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we get to the 9, we're out of symbols, so we go all the way back down to 0, and then we add 1 in our left column to get 1, 0. Now we call that 10, right? But it's because it's one whole group of 10 and no ones left over. We can get all the way up to 19, and then that becomes 20, but it's 2 10s and no 1s. So every 10th number we start over again. And then when we count all the way up to 99, we know that we're out of 10s and 1s, so we need to move over to the next column, the hundreds place. So we have 100, no 10s and no 1s. Yes, Mr. Bossert, I know how counting works. Okay. We know that it's very familiar. We know that if I have 1, 2, 3, 4, 5, we know that that would mean 1 10,000, 2 thousands, 300s, 4 10s, and 5 1s, and we add all those together, the expanded, we get 12,345. But the reason, again, that those places are what they are is because it's base 10, and the 1's place is 10 to the 0 power is 1. 10 to the first power is 10. 10 to the second power is 100. 10 to the third power is 1,000. 10 to the fourth power is 10,000. And etc., etc. Every next place in the system is the next power of the base. So back to Homer. If we had 8 fingers like Homer does, and we decided to start over every 8th number instead of every 10th, okay, then we would have a base 8, or is known as, instead of decimal, it's known as octal counting. Octal meaning 8. In this system, there are 8 symbols to work with. Okay, we would have 0, 1, 2, 3, 4, 5, 6, and 7, and we wouldn't need 8 or 9 at all. So out of the 8 symbols above, we represent every possible number. So we start by listing all of the numbers after 0, 1, 2, 3, 4, 5, 6, 7, and then instead of writing 8, again, the number 8 would not exist in base 8 system. It would be 1, 8, and no 1s. And then, so we wouldn't even say we would write 1, 0. That actually means 8. 1, 8, and no 1s. And so we wouldn't say 10. We wouldn't say 8 either. We would say 1, 0. Okay? Because it's not 10 in base 8. This number that I've written above here, 310, notice I'm not calling it 310 because that's not what it is in base 8. And this little subscript down after the number is often used to tell me what base I'm working in. Now I don't normally write these out, but for our purpose, so that we understand how it works, this is indicating a 0 here is indicating 0, 8 to the 0s or 0 1s. This 1 is indicating 1 in the 8 to the first or 8's place. And this 3 is indicating 3, 8 to the seconds, or 64s. So this number itself is 3 64s and 1 8 and no 1s. So if you can see below here, I've got 3 64s is equivalent to 192. Plus 1 8, that's 8, plus no 1s, that's 0. So this is the number we would know as 200, but in base 8 it's expressed as 310. Right? They mean the same thing, but this is a different number system, so we would number it a little differently. 310 would be equivalent in base 10 to 200. Okay, so again, this is talking about counting in base 8. 1 1 would not mean 11. It would mean 1 8 and 1 1, so that's 9. 1 2 would mean the same as 1 8 and 2 1s, which would be 10, and so on and so on. We'd hit 1 7, again that's 1 8 and 7 1s, so that's 15. And 16 is the same as 2 8s and no 1s. So this number 20 wouldn't be 20. It would be 2 8s and no 1s. It's really 16. So we would obviously we would be moving forward or progressing through the places more rapidly because the 8s turn over a lot faster than the 10s do. When we get up to 7 7, the next number would not be 7 8. Again, there's no 8 in there. We would be at 1 0 0. So the numbers would go from 7 7 to 1 0 0, because 7 7 means 7 8s and 7 1s. That's 56 plus 7 is 63, and so the next one is the next power. It would be 100. This would mean 64. So when I write the octal number 1, 2, 3, 4, 5, I mean 5 in the ones place, because that's 8 to the 0 power is 1. 4 in the eights place, because 8 to the first is 1. 8 to the second are 64. 3 in the 64's place. 8 to the third is 512. Now you might not know that, but that's what it is. 64 times 8 is 512. Two of those. And then that times 8 would be 8 to the fourth, or 4,096, and there would be one of those. So this wouldn't be 12,345. This would be 4,096 plus 2 times 512 plus 3 times 64 plus 4 times 8 plus 5 times 1, etc. And you see that I have 496 plus, this is 512 times 2. This is 3 times 64, this is 4 times 8, and this is 5 times 1. And that would be the same as equivalent to in base 10, 5349. So this in base 8, 1, 2, 3, 4, 5, would be equivalent to that. Now again, if you are confused with this, you can go back. We're going to, as you get the notes down and we'll continue working, it will make more sense to you but you didn't learn to count in a day, you didn't learn to place values in a day. So we are asking a lot out of you. All right, but you're bright, you'll be able to pick it up, I think. So what does the number mean in base 10? So if I look at this number, try to resist the urge in this unit of calling this 23, because it's not. We've got two places. The first place is always the ones place, because this would be 8 to the 0. And the second one is going to be 8 to the first, or the eights place. Right? So there are 3 8 to the 0s, or 3 ones. And there are 2 8s. And so 2 times 8 is 16, plus 3 times 1. 16 plus 3 is 19. So in base 10, it would be 19. 1, 2, 5. Again, see if you can come up with what the base 10 value of 1, 2, 5 in octal or base 8 is. Okay, hopefully you're applying this now. The first place in base 8 would be the ones place. So this would be 5, would be 5. The second place is the eights place, so 2 times 8 is 16. And the third place in base 8 would be 8 to the second, or 64, and one of those would mean 64. So if we expand those out, 64 plus 16 plus 8 is, plus 5, excuse me, is 85. Okay, so now we're experts at base 10. We're learning base 8. Any number would work. We can have a base anything. But another one that is pretty standard that computers actually use, and we'll talk about why that is base 16, or hexadecimal. So this is a good word to write down. Hexadecimal is base 16. The big problem is that as humans, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We don't have a number that represents 10, because when we get to 10, we put 1 in the tens place and 0 in the ones place. So we don't actually have a number that represents 10, or 11, or 12, or 13, or 14, or 15. But we need all of those in the base 16 or hexadecimal system, because we need a symbol that represents all the way up through 15 before we get to a 16, which would be, I just made air quotes, you can't see that, but a 16, which would be a 1 in the next column. So we use, when we get to 10, we use A. That's the number that we call 10. B would represent the number we call 11, C would be 12, D would be 13, E would be 14, and F would be 15. Now, I don't always memorize that. I know that A is 10, I know F is 15, and I kind of figure out from there. But it'd be a good idea for you to understand that. So we look at this 2, 1 here in base 16. It means the first place would be 16 to the 0, which is always the ones place in all these number systems. And the second place would be 16 to the first, or 16s. So this means 2 times 16, 32, and 1, 1. So this is equal to 33 in base 10. Alright, see if you can come up with what this means. 4C. Alright, again, if we think about what the places mean, this is the ones place, and this is the 16th place. Now I really encourage you to, until you really have a good understanding, handle on all of these, that you list out what the places are when you're dealing with these. The 10s you don't need to know base 10 because you know that one already, but for these other ones, until you really have this under control, figure out, list what the place values would be. If I had to do the next place value, would be 16 to the second or the 256s. And we don't have any there of this one, so we don't worry about that. But C means A is 10, B is 11, C is 12. So 12 ones and 4 in the 16th place. 4 times 16 is 64, and 12 times 1. So together this should be 76 in base 10. Very good. There it is. Alright, so binary or base 2. And again, I think we understand or know that this is how computers were, they started with base 2, or binary code is what they, and again, the reason computers use that is because they go through a program, and the program for each line of code, it's asked to make a decision, either yes, this condition applies, that would be like a 1, or no, the condition does not apply, that would be a 0. So the computer can decide yes and no. It can't make more kind of complex decisions than that unless you program it. And that, but again, it's just a system of 1s and 0s, yeses and nos, open and shut. And since I know my powers of 2, right, I have this big number, 1001, 0101. Now, you know when we have like a big number like 42,822, let's say we put this comma as a grouping placeholder, so it's easier for us to see. In the base 2 of binary, that is indicated by this space in between. This isn't two separate numbers. This is one number, but they have a little extra space in between, and that groups together these 4. And we'll talk a little bit more why that is upcoming. But the places, again, just like all the other bases, the places are that base to the 0 power, to the first power, second power, third power. Every place that you go over increasing is the next power of, in this case, 2. 2 to the 0 is 1, 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth is 32. So you see that all of these places are these things. So this number, 10010101, is 1 in the 128s column, no 64s and no 32s, but 1 in the 16 column. 0 in the 8s, 1 4, 0 in the 2s, and 1 1. So we add all these together, we find out that it is 126, 144, 148, 149. So this is the base 2 number. Yikes. This is the base 2 number, 149. I say that? Yeah, I do. Yeah, I got it right. Okay, yay me. The nice thing about base 2 is, once you know what the place values are, it's not, you don't have to do that thing in base 16 where you would have to multiply like 256 times 3 and 16 times 5 and then add those together. It's either a 1 or a 0, so you either add that place value or you don't. There's no extra things to do. It's going to be important for us to understand when we see numbers that are written in binary to quickly translate those in our brain just like somebody who speaks both English and French almost automatically translates those things back and forth between the two. Counting, right, in decimal, 0, 1, 2, 3, 4, 5, 6, 7, 8, and I've got 9, 10 here. In binary, zero is 0, 0, 0, 0. Now, we could just put 1, 0. But again, they're grouped in a group of 4 numbers usually. So 1, although you could just write 1, a lot of times it has the 3 zeros in front of it. 2 would not be 2 because that doesn't exist. Remember, in base 2, only 1s and zeros. So it would be a 2 in the 1 in the 2's place and no 1s. So 2 plus 0 is 2. 3 is a 2 and a 1. 4 would have no 1s and no 2s, but 1 in the 4's place. So you can kind of see the pattern developing. So 1, 0, 1 means 1, 4, no 2s, and 1, 1. So that's 5. 6 is 0, and then 1, 4, 1, 2, and no 1s. 7 has no, this is the 8's place, right? But a 4, a 2, and a 1 is 7. And when we get to 8, that is 1 in the 8's place and no of the others. 9 is an 8 and a 1. So 8, 1 in the 8's place and 1 in the 1's place. 10, we can see the pattern developing here. And 8, no 4s, 1, 2, and no 1s. That's 10. 8 and 2 is 10. Alright. See if you can come up, see if you can write 11, 12, 13, 14, and 15. Pause it and come back. Alright, how'd you do? Did you say 11 was 1, 0, 1, 1? That's 8. No 4s. 1, 2, and 1, 1. 8 and 2 and 1 is 11. 12 is 8 plus 4, and no 2s and no 1s. 13 is an 8 and a 4 and a 1. 14 is an 8 and a 4 and a 2, so 1, 1, 1, 0. And 15 is 1, 1, 1, 1. For 16, we would have none of those and a 1 now in the next place, which would be the 16's place. It's very important because between base 2 and base 16 we can convert, and we'll talk about that in a second. It's important that we can recognize these numbers 0 through 15 in binary pretty quickly. So that is learning how to count in binary. Up to 15 is important. So that would be a skill, just like when we learned how to count. We want to learn how to count. Okay. Because 2 to the 4th is 16, every 4, and if we take this group of 4, which is again why we had you write them in 4s, every group of 4 base 2 places can hold all of the numbers that you can hold in one base 16 place. 2 to the 4th is the same as 16 to the 1st power. The largest number that exists in base 16 is 15, or F. That's correct. The largest number that you can make in 4 places in base 2 is 1, 1, 1, 1, which is 15. I mean, that's not a coincidence. 2 to the 4th is 16. So every 4 places in base 2, we can describe 1 place in base 16. And this is how we're going to kind of help us convert here. If we look at this number, see, let's do some practice. Practice converting this number in base 2. So what is that number in base 2? What is it in base 10, I suppose we should say? Well, this is the 1's place. There's no 1's. The 2's place is a 1. The 4's place is a 0. And the 8's place is a 1. So we have an 8 and a 2, which is 10. Okay? If we looked at these 4 places together and make it in one base 16 number, we could describe these four as 10 or A. So we can describe four places in one base 16 place. In base 2, this number is no ones, a 2, a 4, no 8s, no 16s, a 32, a 64, no 128s, this is a 256, alright, this is 512, there are 0 of those, this is 1024, there are 0 of those, and this is, what is that, 2048. Would be one of those. So if we want the decimal version of this, we would add those places together. 6, let's go this way, it's probably easier. 2048, I'm going to add these together, and I will be and so if we put the values of the place values from base 2, 2048's place, 256's place, 64s, 32s, 4s, and 2s, this adds up to be 2406 in base 10. Something interesting, again, because we're grouping these in groups of 4s, and every 4 places in base 2 is equivalent to something that we can make in base 16. This is the number that I have below here, 966 in base 16, and I've kind of purposefully spread these out. But 9 256s plus 6 16s plus 6 1s, if we add that together, that is the same 2406. And I want you to see this. If we look individually at the groups of 4, right, you can go back to your counting page if you want in your notes. If you look at 0110, that's the number in base 2, that would be the number 6. And this next group of 4, 0110 again, is another 6. And 1001 in base 2 is the same as 9. So why does it work like this? Well, the first 4 places in base 2, the biggest number you can make is 15. If it was 1111, that would be 15, and that would be the biggest value that you could make. When you get to the next place in base 2, this is the 16s place. And it actually starts the second group of numbers in base 16, would be referring to these. So 16 and 32 and 64, and this is 128. If you had a 16 and a 62 and a 16 and a 32 and a 64 and a 128, that would be 238. Is that right? Let's see. 128 plus 64 plus 32 plus 16 is 240, and that would be 240 would be 1111. Well, 240, if you divide that by 16, that's 15 16s. So the biggest number you could make here would be, in base 16, would be F, or 15, and this is 6 16s, which is the same as 96, which is what you're representing here in base 2. And if you look at this group again, this starts at 256. Well, one here in base 8 is, if you just look at the number itself, 1001, if they're 256s, 8 256s is the same as 2048. So what we can do really quickly is condense every 4 units in base 2 to a base 16. And that's how computers deal with, if they have big long codes, they can condense it from base 2 or binary into hexadecimal to make it fit, right? So you may have something in hex code, which is really binary code, but just a condensed version. So if I have the number 1010, 0011 in base 2, I can take that in base 16 and I can make that A3. Because if I look at these four, there'd be those are the ones digit place in base 16. There's 3 there, and this is the 16's place. This is really 32 and 128. That's really 160, and that would be 10 or A 16s. And the number 1010, this is referring to in base 2 is 10, and starting in the 16's place. So in base 16, there's 10 16s and 3 1s. And you could do it the opposite. If you have 7C in base 16, if you want to make it binary or base 2, you need to take this base 16 number and write it. This C means 12. So we really need to write a 4-place number in base 2. That means 12. And that would be, if you look back to your chart, it would be 1100. And then also make a 4-place number that means 7. And that would be 0111. So to go back and forth between base 16 and base 2, because 2 to the 4th is 16, every 1 place in base 16 is equivalent to 4 places in base 2. This was a lot of information. I appreciate you sticking with it and writing examples and really thinking about the place values. We're going to do a lot of practice, so don't think you have to come to class being a master of this, but we're going to have an open mind and be willing to try to make some deeper connections with this next class. All right, thank you. Namaste.